Morning, guys. This is going to be the beginning of the notes for physics and circuits. And we're going to start with Ohm's law. So Ohm's law tells us that there's a relationship where the resistance is proportional to the voltage divided by the current. Very often, we write this as an equation as V equals IR. And so the current passing through it is always directly proportional to the voltage drop across it, independent of the value of the voltage drop. So the value of its resistance doesn't change, even if we apply a different voltage across it. This is the case for ideal conductors. So unlike Newton's second law, you can't apply this to everything. This is going to be able to be applied to circuit components, and that's it. So this isn't going to work for, say, a person or other things. And we're saying that this resistance isn't going to change, so our resistor isn't going to change in temperature either. So this is a digital multimeter. We'll be using these in class to measure a number of different things, whether it's voltage, drops, or resistance. If we're measuring current, it's known as an ammeter, because you remember that current is designated by a capital I or a lowercase I, and its units are amperes. You actually have to change the port for it to be an ammeter. And we're not going to do that because it's possible for you to blow the fuse in the meter. So we're just going to do voltage and resistance. And the idea is that the ammeter has to become part of the circuit. So the ammeter actually has to be in the path of the circuit. An ohm meter is going to measure resistance. Again, ohms resistance is R or R. Our units are in ohms. And in this case, you're measuring across the resistor, and you can't have it be a closed circuit. So we can't have current running through the resistor when we're measuring what the resistance is. So here's a picture of us measuring voltage, which is going to be very similar to measuring resistance, except this is going to be a closed circuit. And what you're measuring here, we have V, we have the straight line there. That tells us that it's direct current voltage, which is what we're going to be dealing with because we're going to be dealing with 9-volt batteries. And we're measuring the difference between the voltage on one side to the other. So we're measuring a voltage drop. So whatever pressure this battery provides is going to be dropped across the component, across the resistor. Here's a picture of it being an ammeter. Again, the port changed. If you look at the port here, it was in this port. Now it's going to that port. Now this dial has been changed to the straight line. So this is direct current. And if we look at the path of conventional current, which we say is the flow of positive charge, it actually has to go inside of the meter to make it to the other side of the battery. And again, the battery does not provide the electrons. It provides the pressure. Everything that we're connecting a battery to is already completely full of electrons. and they're readily moving. We just give them a push in the direction we want them to go. Then you put components in the way to make it do whatever you want your circuit to do. So in our picture here, we have 2 meters. If we look at what's going on, this one would be our voltmeter. It's connected from one side of the light bulb to the other side of the light bulb. We'd be measuring what the voltage drop is. This one would be an ammeter. The current is coming out of here. It actually goes through the meter, and then it goes back to the battery, and that's part of the path. In this picture, we have just 2 batteries that are both 1.5 volts end to end, which would combine to be 3 volts. If I had all 3 of them, it'd be 4.5 volts. And here we have what the measurement is. So these 2 batteries are 2.49 volts. This is reading 98.8. That wouldn't be amperes. It's most likely milliamperes. So it's 0.098 amperes. An amp is a lot. So if we're talking about like our circuit breakers for rooms in our homes, they're probably 15 amps or 20 amps. So you're not going to get that in a circuit that we're going to be dealing with. We're going to be dealing with much smaller amps. All right, so to draw this, now I can consider this to be 2 batteries, or I can put them end to end and make them 2 batteries. And we're saying that we have the positive and the negative. The negative went to the ammeter in our picture. Then it went to the light bulb, and that was a loop all unto its own. So that is a complete circuit, although we did have a voltmeter, and the voltmeter was measuring the difference in the pressure from one side of the light bulb to the other. So this would be our schematic drawing. All right, so early on, we had batteries that were Leyden jars, which was positive being held on the inside, negative on the outside with an insulator in the middle, and you would be able to dump all of that all at once by touching the 2 together. And we saw that Franklin explained why positive was positive. You guys will have watched the video and answered the questions about Volta and Galvani, but Volta figured out that different types of metals with an acid between them would provide a small potential. And what you could do was stack them on top of each other over and over again, like that electric ray that we saw in the video. And you would end up with metal on top of metal on top of metal in a pile. And we call this a voltaic pile. And you would have one side that was positive and one side that was negative, and you would connect the 2 ends, and it would cause it to flow. Now, when they first did this, they thought this lasted forever, because compared to discharging a single Leyden jar, this charge was continuous and lasted a long time. And you can imagine, if you just experienced the battery for the first time, and maybe the battery lasts for days before it would die if you ran it continuously, you might think it did last forever because you probably wouldn't run it for that long. So the battery provides this pressure. In our water analogy, which they explained this based on water, our current was like water current. our battery was like a pump. So if you've ever seen a pump in a pool, the pump does not supply the water. The pump moves the water. And that's what the battery is going to do for us. It's going to provide that pressure that moves it. You can add batteries together. If you put them end to end, then they just become so there's and we saw an end puzzle on this too of how a battery stores energy as well. But we have a positive side and a negative side. If we connect them two, then we have this pressure, and the current is going to flow throughout the whole thing. So the current flows through the battery as well. If we put them end to end, we would be adding these cells together. 1.5 volt cells are very common. So adding them together, whether it's in our calculator where we have 4 of them, or a flashlight where you might have 2 or 3 of them, or a 9-volt battery where you have 6 of them. So direct current is going to be current just going in one direction. Alternating current is going to be the same electrons just going back and forth. This is what we get from batteries. This is how your phone works. This is how your computer works, like a laptop. This is when you plug things into your house. So whether it's a hair dryer or a coffee maker, it's going to be 120 volts. And these same electrons are going back and forth 60 times per second. Which we call 60 hertz. So hertz is the unit for frequency. If we put something in the path of this battery, we have a closed circuit, and we'll have made one in class. And we say that the electric current is the flow of positive charge. So this is going to be our conventional current, as it's known. In reality now, we know that it's the electrons that are moving. We know that they are in the outside of the atom. Keep in mind, when they explained what was positive and what was negative, and that was done by Franklin, he explained it in terms of bookkeeping. So it's completely arbitrary that it turns out that protons ended up being positive and electrons ended up being negative. When they started studying this circuit stuff in the 1700s, they always talked about the flow of positive charge because that's how he described how the Leyden jar was discharging. So even though we know that it's the electrons that's flowing, to a person, every physics teacher in the world teaches it that it's going the opposite way. And this is known as conventional current. So conventional because we have certain conventions in physics that we agree upon, so we can study things in the same way. Kind of like how up is positive and to the right is positive. We say that the flow of current is the conventional current. So it's going to go from positive to negative. There's really no difference, no discernible difference, whether you consider it to be the flow of positive charge or negative charge for the level of circuits that we're going to deal with. So this is what current is. If you remember our units, we started the year with just kilograms, meters per second. And in the last section, we added a new base unit, which was coulombs, which is going to be our amount of charge. Current is going to be how much charge is going through per second. So it's going to be Q divided by T. The new unit of this is amperes, named after Rene Ampere. Again, this current could be a lowercase I. This Q could be a lowercase q. Our time is going to be in seconds because that's what we've agreed upon, that we're going to be combining these 4 together for all of our units. All right, so a current of 3 amperes is measured in a circuit. How many electrons pass any given point in a second? So this formula, which is known as the definition of current, can be manipulated so that you have current times time. So I have 3 amperes times 1 second is going to be 3 coulombs. And then we know that 1 electron has an electron charge magnitude, so I'm not worried about sign, of 1.6 times 10 to the negative 19th coulombs, or 1.602. We typically just do the 1.6, but you might see 1.602 in other places, and I don't want you to be confused. So this gives us about 1.9 times 10 to the 19th electrons every second. So that's a lot. That's a lot. And when they devised what the unit was going to be for charge, a coulomb is a big amount, a huge amount of charge. Like I said, if we put batteries end to end in series, we call this, we add up the voltage. If you put them opposed to each other, the big battery will overpower. So in this resistor would be feeling 8 volts, and the current would be going that way. So the 20-volt battery would overpower the 12-volt battery. This probably doesn't make sense why you'd ever wire things up backwards, but incidentally, you guys do this all the time. I'm doing it right now. I'm charging my phone with this laptop here because my battery is low. And when you put a battery in a battery charger, you're putting the battery in backwards, and it's forcing the current to go in the opposite direction and put charge back onto the phone's battery. My battery's not lasting very good. So between waking up in the morning and I use it for my run, and then by the time I get to school, it's down to like 40%. So I think it might be time for me to get a new phone. Putting batteries in parallel does not add to the potential, but you can get more current out of it. So sometimes you'll see this. When I was around your age, I worked at a marina, and we stored boats in shelves, and we had forklifts that actually picked the boats up, and you put them up to be 4 high, and they would have car batteries to start the forklifts. These are giant forklifts. The biggest one weighed 76,000 pounds. They would have 2 car batteries in parallel to start it. So it only needed 12 volts, but having that was better than just having a much bigger battery. So that might be the case. I would guess it's probably the same case for big trucks too. The difference between electrocution and shock we looked at in terms of the war of the currents. So electrocution is actually a contraction. It's the combination of electricity and execution. So you saw me shock myself, but I did not electrocute myself because that means running current through you until you were dead. If you become part of the circuit, you can get shocked. So we have someone just touching a wire apparently and becoming a path. This is the symbol for ground. This lady is touching the metal here, and it must not be a GFI there, so there must be charge building up, and she's becoming part of the circuit. So she provides a path for extra charge to go, and that's what's dangerous if it runs across where your heart is. That's why if you're ever stuck in a lightning storm, because it's just as likely that the charge goes from the ground up as up down, and if it hits the ground, it could run through your body. You're best to keep your knees together, so then it'll just go up one knee and down the other knee and not go all the way up into where your organs are. So not having things grounded can cause charge to build up. We used to have a computer down in Cisco that would shock them every time they turned it on. It was because the ground wire from the tower, the metal tower, wasn't grounded. Yeah, so the safest plugs are going to be the ones that have 3. I'll show you guys that in class. And that means that one of them goes to the ground. If we're looking at our outlets, we think about our outlet as a face. The eyes are the hot ones. So that's where you're going to have a difference in voltage. This one is the ground. And so that third plug, and not all plugs will have the third plug, actually goes to a metal pipe that is hammered into the ground in the basement or the lowest floor. And all of the wires go to that ground, and it has to be down so many feet based on what the code is for whatever state you're in. And the idea is that the ground could take so much charge. So it's a good place to dump excess charge, no matter how much you have. Well, so here's someone getting shocked. This person was running from the police. You can see the power people are here. They're turning off the power. They turn off the power down here. So this is at 0 volts. The way power is, the higher you go up, the higher the voltage is. They do this for safety. And so he is at 0 volts here because the power company was able to turn this off, but the higher voltage has to be turned off at a further distance. And so this was higher voltage. I don't know if it's 500 volts or what. And when he becomes a path for the 500 volts to get down to the 0 volts, this is just a second later, he becomes a fireball. This person actually survived. He wasn't electrocuted, but he provided a path. You've probably noticed that we have one of these in the main office and also by the gym. So it's possible to use a large voltage, relatively, and a small current, because remember, current's the thing that's dangerous to you, to stimulate your heart. So that's the defibrillator. And I'll demonstrate this for you, but many things will have sacrificial pieces of metal that will burn in half so that something doesn't get damaged. So it turns out that the faster that current goes through, it has to bump into all the molecules. And by bumping into them, the faster it goes through, they're going to get hotter and hotter. And that's about how electrocution would work, that current goes through, that it's actually the heat that's going to do your organs in. So inside your car, you'd have ones like this, or inside of Christmas lights, you'd have ones like that. And so once the current gets to an unsafe level, that metal will burn in half and it'll break the circuit so it doesn't damage anything more important. These are the kind that used to be in homes. I doubt that any of you guys have homes that have these anymore. But different sizes had different threads, so you couldn't fit a bigger one in for safety reasons. That didn't used to always be the case, which was dangerous. And I'm going to show you guys this as well in class, how a circuit breaker works and the beauty of bimetallic strips. All right, so very often it's useful to